Welcome to the course Algorithmic Design. The topic of this session is space and fields, space in a very general sense. And this is from a book from Vera Bühlmann and Ludger Hovestadt. Well, it's actually inspired by their writings and their lectures, but I didn't really reference them properly here. But basically, and I also always, when I do these historical developments, I sometimes don't, or I try not to really put dates there, because somehow you can Google the dates always on your own. The dates are not that important. It's the sequence is important. Or okay, so kind of we start with the car. Basically the car kind of identified, or he defined space as identical with extension, or so extension is connected with bodies. So in that sense, there's no space without bodies. And hence no empty space. So that was kind of part of his philosophy. But when we say today Cartesian system, Cartesian coordinates, this relates directly to the car. Or so we will basically, yeah, when we work with coordinates, and that's basically the kind of when we work in CAD environment, like in Rhino, we work with coordinates directly. So that this thinking that you can relate sort of shapes and geometry with sort of basically algebra. This comes directly from Descartes. Or so we have him to thank for that. And yeah, and then kind of after Newton, or after Descartes, we have Newton. Somehow this connection that sort of yes, we have space, but then there's also kind of time there, and they are independent, or they are absolute and independent, and space and time have independent existence in relation to matter and energy, and in a way the physical reality is just evolution of this three-dimensional world. Or so of course Einstein had a bit different view on that. So he so kind of physical reality as sort of four-dimensional or space-time. I actually didn't write it here. And there's, in that sense, kind of no space, empty, or field. So somehow this idea of field comes into play, and this then also directly connects these dimensions, or so space-time, so space and time, with energy. That's the famous equation, or E equals mc squared. So kind of the space-time and energy and matter are somehow intricately connected. Then around the same time, we have development of the quantum theory, which somehow postulates this sort of discrete space and time. Or so there's somehow granularity on the scale of Planck's length and Planck's time, and this brings sort of a stochastic also nature to our world. And yeah, so the kind of space and time are not continuous; they are discrete quantities. And this, again, not directly, but sort of a little bit brings us to the digital understanding. Of course, in the very first session, I mentioned that that's how we also have to understand space and time in the computational realm, or at least the digital realm, that we have to discretize both. Or so coordinates are discrete, even though we have some decimal numbers with a finite number of spaces. Those are the kind of the floating point representation of a number. So there is some granularity there, even though it's very fine. And of course, every time we talk about iterations in the context of computation, so I talk about we will iterate through a list, or we will now do certain number of iterations. Iterations just means basically this discretization of time. And then digital also kind of brings us to this sort of reduction to sort of topological relations, or somehow that it's the geometry sort of representation, and the way that things exist in the digital realm, in a way in a computer memory, is in a way topological in nature. Or so these geometrical relations are created from this topological relations kind of. So it's a bit maybe technical, but even, let's say, a further sort of abstraction of what the space is, or that yeah, okay, so those are just sort of let's say philosophical let's say developments of this concept. But in a very practical sense, we'll be using Cartesian coordinates. Or so last time somebody asked me to comment kind of what's exactly on all the on all the pictures, but again, I'm always leaving you so that there's a kind of short explanation of every picture here on the left that you can read later. I'll just try to kind of shortly explain. Also, we will be working, well, in Rhino, we work with a three-dimensional Cartesian space. And sometimes we just reduce it to a two-dimensional plane, depending on the type of problem. And these are so-called Cartesian coordinates, or so we can also translate them sort of into polar coordinates, depending on the depending on what we need. And related, but we'll mostly be using this sort of a free axis system. Also, when I talk about axes, I talk about these orthonormal axes, also x, y, and z. And in order to know which one is which, we use the so-called right-hand rule. And if you would be in a classroom, I would be constantly showing you sort of this configuration of fingers. Unfortunately, we're not in a classroom, so you might just have to kind of imagine this. This is basically how you can, the right-hand rule basically tells us how the axis should be labeled. Or because if I define a plane by having a x-axis and the y-axis, then the z-axis, which is orthogonal to both of these, it's in a way a cross product, I can basically flip it either way. Or so there are two possible solutions. There are two possible sort of two vectors that are orthogonal to these two. But if you use a right-hand rule, then we basically choose one of these. So here this flip z is not shown. Just the kind of, so this is the positive z, and then the other one would be the negative z. Or if you would use the left-hand rule, then we would get the opposite z. Or so this is just kind of to help us navigate a bit this sort of a three-dimensional coordinate systems. Yeah, so kind of when we, again, in Rhino, when we define a plane, we define only two axes, and the third one is then given according to this right-hand rule. That's it. And it's specific, technically, this is the z is a cross product of x and y. Okay, and then here a little bit kind of further on, so something that we will not work with, but it's maybe an interesting digression. So we talk about, you know, two-dimensional space, three-dimensional space, and then we can also talk about four-dimensional space. And I don't really have many references here, but architects have been for sure interested in four-dimensional space, kind of as of course mathematical construct, but kind of in their endeavors. And there was even this very popular book called Flatland, which is now I guess 100 years old already, which sort of it is kind of a story of a two-dimensional world that encounters a three-dimensional being, or so, and it's today used very often as a reference, or kind of to help us sort of extend this thinking from three-dimensional world to the four-dimensional world, or so-called kind of Minkowski space. And yeah, recently I know that there are even some in the entertainment industry, there are some games that exploit this concept of sort of four-dimensionality. This is not directly related, but a little bit kind of points to the topic. The next time that we'll work with is curvature of space, or so we can talk about curved objects in three-dimensional space. So two-dimensional manifolds which are curved, embedded in three-dimensional space. But when we talk about three-dimensional manifolds that are curved and embedded in four-dimensional space, then it's very hard to wrap our head around it. Basically, then we talk about space-time and so on. Okay, so that's a little bit kind of when we talk about dimensions, we can sort of push it even further, but we will not really work with these ideas. It's just I wanted to point out that for a computer, all of these concepts are so programmable, or so the same way that we can program a plane, we can program kind of three-dimensional space, and then we can actually program four-dimensional space. And today we will also work a little bit, for example, with color. So we will have a coordinates in 3 dimensions, and then additionally to that, every point will have a color, which means that somehow we have these 3 extra color coordinates which are attached to it. So you can sort of think of it as a, you know, spatial and kind of color space, or objects existing in sort of, yeah, maybe in some way in kind of a 6-dimensional space or so. These topics kind of are a little bit related. Of course, this brings us to the very, very big topic of linear algebra, but we will not really work with matrices, or we will just work with vectors. Also, somehow this idea that vectors are arrows in space, and here I listed just some operations. So this is a 2-dimensional vector, a 3-dimensional vector, and then we can add them together. This is how you add vectors A and B. This is how you can subtract them. We can scale vectors. So this is called, actually, this is a, yeah, this is kind of a scalar multiplication. So we kind of scale the vector, we make it longer or shorter, or we can also flip it by multiplying it with a negative number. And then this is the dot product, and this is the cross product. So I mentioned before that according to right-hand rule, if I have a cross product of x of A and B, I get basically the z-axis of it. And then if I flip these, I get the opposite ones. Or so it's a non-commutative operation. Yeah, well, all of these might actually come when you work with when you work in the realm of computational design. You have to be very, very comfortable with vectors. There are some other ways that you could sort of deal with translations in space, but the vectors are most convenient for us, and we will use those. Or so you have to kind of learn how to kind of deal with them in your head. Okay, and this goes a little bit beyond. So not really the topic, but it's kind of underlying everything. This idea of a vector space. Or so, if I imagine that my space contains points, and then every point is in a way represented as a point vector, or so there's a vector that goes from origin to that point. So in a way, the origin is translated to the point. Then we talk about vector spaces, and then linear algebra gives me tools to basically transform, to describe transformations of these vector spaces. And again, indirectly, this is used in basically all graphics. So every time you open a 3D program that kind of displays meshes or anything 3-dimensional, basically this is the underlying mathematics set. But for us, why this is sort of useful is so in mathematics, you would kind of, this is how you would write a vector, or kind of, you know, use this vertical notation, and you would use a horizontal notation to write to display points. And in Python, specifically in Rhino, these of course, we cannot write in vertical. So for us, everything will be horizontal. So we can sometimes exchange. Basically, it's the same notation for vectors and for points. And we can almost use them interchangeably if we imagine points as being point vectors. So maybe even today, at one moment, I will use I'll write like a formula using vector math. And then I'll try to maybe draw it to explain kind of how the formula works, but it's basically just doing some calculations with vectors, and yeah, this kind of idea that points can also be represented by vectors is then important to kind of understand. Okay, and hope I didn't kind of scare you with all this math, but you will see a little bit kind of how it works in practice. But yeah, a little bit of math gets you already a long way. So there's no time wasted on kind of brushing up a little bit that high school maths. Okay, and then the second kind of a big topic today is the field. What is a field? So this is sort of my kind of a explanation of what the field is. There's of course different definition of a field in physics and different in mathematics. But here I kind of try to just relate a little bit to computational design. So field is in a way a construct. It's a mathematical object, has many applications in fields outside of mathematics, like for example in physics. And we will also in a way use this field concept. Field has dimensionality, or so there's some dimension attached to it. It can be like a number line is a 1D field. A complex plane is a 2D field, and so on. So 3D fields is basically space. So when I say space, I mean 3-dimensional field. And when I say a plane or a field, I mean kind of a 2-dimensional plane in that sense. Okay, the field is continuous, or so we can kind of infinitely divide it. without gaps, and all points are well defined except in singularities. Or so sometimes fields contain singularities and we have to deal with them. And even in our example that I'll try to do today, singularities might appear. Those are points where certain values, so values of the field might reach infinity, and we will use some tricks to avoid these singularities. And in physics, this is called renormalization. So you need to kind of renormalize your field in order to avoid this inconvenience, let's say. Okay, but otherwise, except in singularities, kind of field is well defined in every point. Okay, and then these field points, or points in the field, they correspond to values. And these values can be either just a number, then we just call it a scalar, or they can be vector values. And again, if you think a little bit, what is an image? What is a color image? It's a field of points or pixels. Every pixel has a color. And what is a color? Color is basically a three-dimensional coordinate in a color space, for example, RGB cube. So that point has a coordinate, but it also has a color coordinate, or in that sense, you can think of it as a vector. And in that way, colored image is already a multidimensional field. And that's when I say field, that's what I mean. Or so it's a bit of it is kind of an overlay of different, let's say, numbers and vectors. And of course, if you go further, then these are basically kind of tensor fields. And this idea is very powerful because you can use it to describe many things that happen in the physical world. For example, you can describe stresses in a material by using tensors. Or so there's a material or kind of atoms or material points in a way, and then they have certain stresses associated with them, which are sort of forces that act in different directions. Okay, and in a sense, again, a colored image is also a field. Okay, here I actually drew it a little bit. So examples of a kind of a scalar field, this one here, vector field, or a tensor field. Or so it's basically just a collection of numbers. And then fields have different properties, like, for example, curl or divergence. So how much the vectors in this field sort of curl or kind of rotate, and how much do they kind of flow into each other or out of each other, measures the divergence. And these ideas kind of in architecture, they kind of went into architecture also through thinkers like, for example, Stan Allen. This is drawings from his book. The book is Field Conditions, and I actually attached at the very end as a reading for you. So we also have it in our collection of texts, and he's kind of using the concept of a field to describe then certain conditions that happen in architecture specifically, and relates a little bit to art. So that's the reading for the end. This is the example that we'll try to do today. It's called field averaging, or at least that's how I call it, where we will define our field as sort of containing, it's going to be a two-dimensional field, and we're going to define some vectors inside, and then we will define sort of a flow lines. We'll kind of average these vectors in a continuous way across the field. And yeah, for that we'll do kind of a few math tricks, and yeah, and that's it. So this field has certain properties, like, for example, we can define these flow lines, and these flow lines never intersect, or so yeah, that's it. They never intersect. They're kind of their density changes, but there's never an intersection of these sort of flow lines. And so we'll try to do this example, and then yeah, then kind of this is something that we will not really do, but it kind of continues from there. Once when we define flow lines on a vector field, then we can map certain properties of it, and this is related specifically to functional analysis. Kind of a vector analysis on vector fields, so we can measure the divergence of the field. So how much do the vectors kind of diverge from each other? Convergence, which is the opposite. Parallel flow, clockwise curl, anti-clockwise curl, so vorticity of the field, and shear flow. So it's kind of a opposite of the parallel flow in a way. Okay, and these ideas were then used in also in kind of art and architecture. On the top left, you can see this is called this piece is called Fractured Landscape. It's from an artist called Jean-Pierre Hebert, and he's kind of one of these early algorithmic basically artists. He founded a group called Algorists, which work with basically code to produce art pieces, and this is in a way sort of a this is kind of drawn on paper with a pen plotter, but it a little bit shows like these kind of a wavy lines. So it's sort of a simulation of a fabric or maybe a terrain, I'm not sure. Then we can use these ideas of a field to create sampling. So here on the right, there's a mural from Knowlton and Harmon, again from 1966. So some of these guys are, I mean, they're doing this already for half a decade. In a way where you associate every point or kind of associate every kind of pixel, grayscale pixel, with a symbol that kind of has a corresponding grayscale value. And yeah, this is called sampling. So you can kind of recreate images using different symbols. Of course, it's also used in like just normal printing as a printing process. And then these fields can be three-dimensional, so we can kind of layer them to create three-dimensional fields. And this was one example from one of the previous courses of this, or one of the previous algorithmic design courses and studios, where you can kind of define sort of a landscape that has, of course, height, so basically a terrain, and then we can map a downhill direction on that sloped terrain, or so we can make kind of particles go down that sloped terrain, and it's in a way simulating rain, or so kind of how the rain would kind of flow down the terrain. And even though, of course, we always imagine a sloped terrain as a three-dimensional object, you can also think of it as just a two-dimensional field that has a gradient, or the gradient is just shows the direction of the slope, which is, again, it's a vector that shows where the water should flow, where it is, the slope direction, and then you can simulate everything in just 2 dimensions using a vector field. Or you can represent it again as a three-dimensional field, basically a terrain. Or so you can kind of play a little bit with these dimensionality concepts when you work with fields. Okay, this is another example, so-called metaballs. They are used a lot in computer graphics. They are also an example of so-called functional surfaces. So, and I'm not sure if you'll have time today to do them, but we can define sort of a point influences, and then we can define a surface, which is like an isosurface that kind of sort of envelops these 2 points, and we define it in a way. We use the same formula as for electric charge, or that's why I put these references here. If these 2 would be point charges, then we can describe a magnetic field around these 2 points using these basically isosurfaces. They would look basically like kind of metaballs. And so we can use to simulate, again, magnetic fields, but in computer graphics, they're just used to create these sort of blobby shapes. So it's, again, hard to see, but there's actually a direct correspondence between these surfaces here and this kind of a magnetic field here. Or so these are, in a way, kind of a gradient lines of this field here. So there's kind of a correspondence between these metaballs and electromagnetic fields. And this is another example. This is called the Cassini Oval. So it's a little bit, it says here, it's a kind of a quadratic plane curve defined as a set of points in the plane such that the product of distances of two fixed points is constant. To be honest, I'm not 100% sure, but I think these, I didn't look into it well yet, but I think these, there's again a connection. I think these metaballs are basically these Cassini ovals. It's just that somehow when you look into literature, these two shapes will never be directly connected, but from my own research, I think they are actually connected. So you kind of also look a little bit into that yourself. But I think these Cassini ovals and these metaballs are actually the same shape. But they somehow come from completely different fields. That's why they are maybe not always directly connected with each other. Okay, but then basically using these principles, you can simulate then, for example, this layering. These are the tree rings. Tree rings are around kind of two merged trunks, so you can simulate those. And there's an office called Soft Lab, which kind of uses a little bit this principle for this digital fabrication project. This was an interior project for, I think it's a gallery in New York, where you have layered plates. So then when they are milled in these blobby forms, you can actually, you can get this sort of kind of blobby shapes, and they are in a way, again, directly related to these metaball shapes. So there's somehow some references here sort of from nature, some from kind of digital fabrication design or design in general, and kind of mathematics. These have kind of also similar aesthetics, but also a similar way that they are, or similar rules that kind of govern them, or how they are created. So they're for sure kind of linked. Okay, and this is an example, goes a bit beyond. So we will not really do it, because we have to, at one moment, move on, but I'm just throwing it out there. So there's there are these called Turing patterns, or specifically reaction diffusion systems. Basically, you can kind of simulate sort of an interaction of sort of concentrate. You have two chemicals, and they interact in a way. One of them is accelerating the reaction, and the other one is kind of inhibiting the reaction. And depending on the concentration of these two chemical components, you can get different patterns. So you can use this to basically simulate these. These are today called Turing patterns, because they were first described by Alan Turing, or the father of modern computing. They also appear in nature. So this is a let me see, left is there. This is like a baby shark, I think, and somehow the way the scales are distributed along its skin it's somehow directly related to these Turing patterns. And there's at least one artist, I'm not sure if he's an architect or an artist, Jonathan McCabe, who actually used these reaction diffusion systems to create kind of patterns. So at one moment in this course, you will have to do your own, sort of develop your own mini projects. And I put this kind of reference here because I think that this might be kind of a good starting point. Also, you might actually choose these reaction diffusion systems and look into kind of how you can simulate them and create basically to create kind of patterning systems. So it is for sure possible. But we will not look at them directly in this course, because time is short. But again, if you're interested in it, I can give you maybe some other references. Okay, and this is actually the last slide. These are the two texts that I chose for today, or for you to read until next week. The first one is Earth Moves: The Furnishing of Territories by Bernard Koch from '95. And it's a rather short text that relates a little bit to this sort of thinking of sort of fields. And incidentally, the title, or the title page, includes again kind of pictures of these let's call them kind of a metaball blobby-like shapes that are kind of that I just sort of described here. And the other text is Field Conditions from Stan Allen from '97. And just go back. So these drawings here are directly from his book, also somehow relating this idea of sort of field thinking to basically certain architectural or kind of urban conditions that happen. So that's a very good kind of maybe text that relates these concepts together. And this is actually not really this is a text that is short text that is reprinted from his book. So there's this AD Reader, the digital turn in architecture, that kind of contains sort of just a part of the text from that book.